Welcome back. Today we're going to be looking at keys in Python. So of course keys are used to make sure that things are secure and people can't access them. And a large part of using keys in Python is the cryptography module, which is depended on by many things that need to make sure stuff is secure. And we're going to specifically look at Fernet keys, which is a specific type of symmetric encryption key. And by using this key, you'll be able to keep your data secure so that only someone with the key can decipher it. So the way this is implemented is that it's built on top of a number of cryptographic primitives. So these are things that are already made and are used a lot in cryptography. And so it uses AES and CBC mode, and it has a 128-bit key, and it uses padding. And then it uses SHA-256 hashing to authenticate the message that's been encrypted. And it says initialization vectors are generated using os.urrandom, which generates random hashes. It does have some limitations, and the main one is that it can't encrypt very large files. However, we're not going to be looking at these kinds of tremendous files, we're just going to be looking at small ones, but this is something to bear into account. If you ever need to encrypt massive amounts of data, this is not the way of doing it. And interestingly, the cryptography module is used in the Python SSL module and requests. So if you ever want to make requests using Python, then you actually use the cryptography module under the hood. So the first thing we're going to do is say pip install cryptography. But you probably have it installed either because you have another module installed that requires on it, or it's just already there. It's a very common module. So the first thing we're going to do is say from cryptography.fernet import Fernet, which is the key. And we're also going to be using pickle and JSON. And so we'll say that our key is fernet.generateKey. So it's just going to generate a random key, and we can just print the key and see that if we run the code a few times, it gives us different keys. And they look like, oh, they're fairly similar because they end in an equal sign. But of course, they're massively different. We then want to transform the key into a Fernet key. So we use initialize Fernet with a key, and we just print F. And it's quite common to call it F. And you can see that we've got this cryptography object, and they look indistinguishable just based on the key. But now we want to save the key, because if we're going to encrypt stuff, we need to encrypt and decrypt with the same key. So we'll say with open fernet.key, and we want to write bytes. And you can see here there's this B at the start, and that's to say that this key is a series of bytes. It's just because the bytes are between 0 and 127, it looks like they're characters. And we'll just call this file and write the key to the file. And so now when we run it, we can see that it's created this fernet.key file, which has our key in it. And if we ever want to reuse it, then we can just repeat. And for consistency, we can no longer generate the key. We can say with open fernet.key read bytes, because we're reading from it as file. F is not fernet from the key, it's from the file.read. And we can print F and check that everything is all working. And obviously we cannot tell because it does not tell you the contents of the key. And this is something that we should keep really secure and never share with anyone, or the label they'll be able to decrypt our stuff. So next we need some plain text, and we'll just have this dictionary called username, and the username could be admin, because some places have this as their username, and the password is going to be password. So it's not actual data that someone is using, hopefully not, but it needs securing. However, we need to convert this into bytes. So we could do that using pickle, but it'll be a lot easier to use JSON, and dumps this to turn it into a string, and then turn it into bytes, and set the encoding equal to UTF-8. And it could be ASCII because we haven't got any special characters, but it's just a good standard to set it to that, just in case the username has special characters in or the password. And then we'll say that the ciphertext is f.encrypt the plain text, and we can just print the plain text and the ciphertext. And you can see the plain text is this, and the ciphertext is this very long thing that has been generated. Actually, if we run it twice, the thing that has been created is actually slightly different. And this is because it's involving a timestamp. So you can actually check information about when it's been encrypted. But if we remove this and say that we also are going to print f.decrypt the ciphertext, which can also be called token because it's a series of tokens, you see that it encrypts and decrypts to the same thing because we're using the same key, which is stored in this file. We could then save this encrypted thing to file, so we can say with open, and we'll call it details.txt, because even though it was initially a JSON file, you see that this string here no longer resembles JSON in any way. And telling someone that it's JSON might give away clues about how they might decrypt it. It's also bytes, so we need to write bytes. We're going to say as file.write ciphertext. And that should be a W because we are writing to it. And if we open details.txt, we get the information we've saved. So when we delete this and all the encrypting methods, as long as we've got the key, which we've got here, we can then open our details.txt file, and we're reading from it this time, and we see that our token is file.read, so it's now a series of tokens, and then we can print f.decrypt token, and you see that we've now recovered this from this file, which is very cool and very useful, and it means that you can share this, and as long as you don't share both this, as long as you don't share the key, which you should definitely never share, you can now access your passwords and usernames without having to worry about someone else reading them. And at code, you don't ever have to print this. You could just say, go to a website or a web server and sign in with the password using the dictionary and never printing the value to the screen. The Fernay module, however, has a few other cool things that I want to show you, and they're not as useful unless you're looking at using them on a professional scale, but they are very cool to know about. So we're actually going to have this new import called multi-Fernay, and we're going to say now that the message is secret message, and the B there just says turn it into bytes. We're also going to have two keys. So our first one's going to be Fernay.generate key, and the second one's going to be the same, and they're going to be different because it generates them randomly or pseudo randomly and makes sure that the probability of them being the same is impossibly small. And so what we've done, if we've combined these keys in the list and created this multi-Fernet object, which takes a list of keys. So if you ever wanted to increase security, you can just add more keys. I'm sure you might have a shed that has a lock on the door, and maybe there's like a gate as well, and you need all the different keys to get through all the different layers of security. Or in a building, and you need multiple key cards to get to multiple areas, and that's how you can make sure something's secure. So we encrypt it to create the token, and then we can print our token, and we can print f.decrypt token. And you can see we've got this token and this secret message. And then you could, for example, keep this key in a web location that you download at runtime, and maybe keep this key on the drive, and then maybe have another key that you store as an environmental variable. And so maybe someone can access one of the keys if they're quite clever, but accessing all three would be impossible, and they'd never be able to decrypt your messages. So you can see that is a very cool way of adding layers of security to your data. And the other thing that we can do is even more complicated and involves quite a few more imports, but it's very useful to do if you're ever doing this in an industrial setting. So from cryptography, from hazmat, primitives, KDF, KB, KDF2, I want to import this massive thing, and I'm very glad that it auto-completes them for me so that I don't have to type them all out. And also from primitives, we're going to import hashes, which is easier to remember. We also need to import base64 and OS. So now, as well as a message, we're also going to have a password. And to make things simple, my password is going to be password, which isn't very secure, but never mind. This is just a demo. And we're going to redefine and say that we have this salt, which is os.urandom, so just randomly generating 16 characters. And if I just print the salt, you can see the kind of things it's generating. And they're just random bytes. And there are 16 of them because I specified. And occasionally, we get an L because it's picked one that happens to be an ASCII character. But they are just random numbers. And some people might set a specific salt, but generating a random salt adds another layer of security. So we've now got a salt and a password that we want to combine. And so we're going to use this huge thing that we imported, and it's asking for all these different things. So our algorithm is going to be hashes dot SHA-256. So this is a hashing algorithm it's going to use when encrypting. The length is 32 because that's what we're setting it to. The salt is just the salt because that's what we defined it to be. Iterations. So the iterations, the recommended number is at least 390,000 for various reasons. There we go, I had an extra 0. Obviously, the more secure, and it's recommended that you do this as much as you can, but we're just setting the iterations to that so it runs a bit quicker. So now we need to generate a key, and this is a bit complicated because we need to encode the new password. This is generating a key from the password. And then F is our Fernet key. And maybe you need a password to decrypt, or maybe you could have the password just stored somewhere random, and someone who steals your data will not know the password and not be able to encrypt stuff. And then here we can just use exactly the same lines of code to encrypt our message, and you can see that it's managed to decrypt it as a secret message using this password. And we could do all this after encrypting it, and create another one, which is going to be a Fernet key, but instead of password, we'll have like a different password, and we'll just put a capital P there, and so it's now a different key. And actually, we're going to use the same KDF, so everything's the same except the password. It's got a capital P, and now we'll try decrypting it again, and you see we get oh, they can only be used once, and you can see that you can't get another key. And in fact, if we even use the same thing, it's now saying invalid token because it tries verifying that it's been decrypted successfully and it has failed. And of course, if we change the password, it works again. So you can see that there's lots of different things you can do to make sure everything is secure. The best way, of course, is having a single key, and that's probably going to work for all the programs you need to use. It's only when you start needing security, because maybe you have some kind of application that's having thousands of users and stores important data, that you need more complicated security. So hopefully you've enjoyed this video, learned how to do encryption using Fernet keys and Python, and I'll see you again, same time next week. Till then.